Now we will see the solution of wave equation using the method of separation of variables. Consider the wave equation dou square y by dou t square equal to c square dou square y by dou x square. Assume that the solution y of xt is of the form y of xt equal to x into t, where capital X is a function of small x alone and capital T is a function of small t alone. Now we evaluate the partial derivatives of y. Dou square y by dou x square equal to x double dash into t. Dou square y by dou t square equal to x into t double dash. Substitute these in the wave equation. X into t double dash equal to c square x double dash into t. Rearranging, x double dash by x equal to 1 by c square t double dash by t. The left side of this equation is a function of x alone and the right side is a function of t alone. So this equation is true only if each side of the equation is equal to a constant. Let that constant be k. So the left side becomes x double dash by x equal to k and the right side 1 by c square t double dash by t equal to k. This gives us two ordinary differential equations for x and t. X double dash minus kx equal to 0 and t double dash minus kc square t equal to 0. Both are second order homogeneous linear ODE. So we can solve them using the roots of the corresponding auxiliary equations. The auxiliary equation for the first ODE is m square minus k equal to 0 and for the second equation is m dash square minus kc square equal to 0. The solution of the above auxiliary equations depend on the value of k. So there arises three possibilities. The first possibility is when k greater than 0, second is k less than 0, third is k equal to 0. So if k is greater than 0, we can write k equal to p square for some p. Then the auxiliary equations becomes m square equal to p square and m dash square equal to c square p square. The roots of the auxiliary equations are m equal to plus or minus p, m dash equal to plus or minus cp. Then the solution of the ODEs are a capital X equal to c1 e raised to px plus c2 e raised to minus px, t equal to c3 e raised to cpt plus c4 e raised to minus cpt. So the solution of the wave equation, which is the product of capital X and capital T, becomes y of xt equal to c1 e raised to px plus c2 e raised to minus px into c3 e raised to cpt plus c4 e raised to minus cpt. Then when k is less than 0, we can write k equal to minus p square. And then new auxiliary equations are m square equal to minus p square, m dash square equal to minus c square p square. Then the roots are m equal to plus or minus ip, m dash equal to plus or minus icp. Both are complex roots. Then the solution of ODEs are x equal to c5 cos px plus c6 sin px and capital T equal to c7 cos cpt plus c4 sin cpt. So by the method of separation of variables, the general solution of the wave equation is y of xt equal to c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt, since the solution must involve trigonometric terms. So to evaluate the position function of any specific situation, we need additional information. That means we need some other conditions, and they are known as the initial conditions and boundary conditions. Initial conditions at t equal to 0 are initial displacement and initial velocity. They are y of x0 and dou y by dou t at x0. These are known as the initial conditions. And at the end points of the string of length L are fixed at all times. So its displacement is equal to 0. So the boundary conditions for the problem becomes y of 0 t equal to 0 and y of L t equal to 0. So these are known as the boundary conditions. Now we can see an example. In this example, which is a vibrating string with the given initial displacement and 0 initial velocity. There are different cases we can consider case by case. A string is stretched and fastened to 2 points at a distance L from each other. Motion is started by displacing the string in the form y equal to a sin pi x by L, from which it is released at time t equal to 0. Show that the displacement of any point at a distance x from one end at time t is given by y of x t equal to a sin pi x by L cos pi ct by L. For solving the above equation, first you write the wave equation. Dou square y by dou t square equal to c square dou square y by dou x square. Next, you write the boundary conditions. Boundary conditions are y of 0 t equal to 0, y of L t equal to 0, because the string is L distance apart. Next, we will write the initial conditions. Initial velocity is given as 0 and the initial displacement is given. That is y of x0 equal to a sin pi x by L. That is given. And initial velocity dou y by dou t at x0 equal to 0. Next, we have to find the displacement. You write the general solution of the wave equation. That is y of xt equal to c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt. Next, we apply the boundary conditions one by one. First boundary condition is y of 0 t equal to 0. That means here x equal to 0. Put x equal to 0 in the solution of wave equation. We will get c1 cos 0 plus c2 sin 0 into c3 cos cpt plus c4 sin cpt. So that's equal to cos 0 is 1, sin 0 is 0. So it is equal to c1 into c3 cos cpt plus c4 sin cpt, which is equal to 0. This is the first boundary condition. Then the product equal to 0 means the possibility is c1 equal to 0. Substitute the value c1 equal to 0 in the solution of the wave equation. It becomes y of xt equal to c2 sin px into c3 cos cpt plus c4 sin cpt. Next, we apply the second boundary condition, that is y of L t equal to 0. That is, put x equal to L in the above equation. So it becomes y of Lt equal to c2 sin p into L bracket c3 cos cpt plus c4 sin cpt is equal to 0. Then this product equal to 0 when sin pl equal to 0. Here c2 cannot be equal to 0 because if c2 equal to 0, the original solution of wave equation becomes meaningless. So the only possibility is sin pl equal to 0. Solving this equation, we will get pl equal to n pi or p equal to n pi by L, where n is an integer. Substituting the value of p in the equation y of xt, in this equation y of xt becomes c2 sin p replaced by n pi by L, n pi by Lx into c3 cos n pi by L ct plus c4 sin n pi by L ct. Wherever p, replace p by n pi by L. So we have applied boundary conditions. Now we have to apply the initial conditions. For that, we need the derivative. So we can calculate dou y by dou t is equal to C2 sin n pi by Lx into nc pi by L into minus C3 sin n pi by L Ct plus C4 cos n pi by L Ct. Now we can apply initial conditions one by one. So apply the initial condition dou y by dou t at x0 equal to 0. That is, you substitute t equal to 0 in the above equation. So dou y by dou t at x comma 0 equal to C2 sin n pi by Lx into nc pi by L into minus C3 sin 0. Put t equal to 0 plus C4 cos 0. Sin 0 is 0, cos 0 is 1. So it becomes C2 C4 nc pi by L into, there's a term missing, sin n pi by Lx. Equate this to 0. Then the possibilities are either C2 equal to 0 or C4 equal to 0. If C2 equal to 0, the solution becomes y of xt equal to 0, the trivial solution. So the possibility is C4 equal to 0. Then the solution becomes y of xt equal to C2 C3 sin n pi by Lx into cos n pi by L Ct. The above function is a solution of the PDE for any integer value of n. And we know that the sum of all such function is also a solution. If n equal to 1, that is a solution. When n equal to 2, that is again a solution. When n equal to 3, that is again a solution. That means if you sum all these values, that is also a solution. Okay, that is the superposition principle we have studied earlier. If one is a solution, the sum is again a solution. So you denote C2 C3 by another constant Bn. Then the new solution found by adding all the above is y of xt equal to sigma n equal to 1 to infinity Bn sin of n pi by Lx cos n pi by L Ct. Finally, we will apply the remaining initial condition, that is y of x0 equal to a sin pi x by L, that is given. So put t equal to 0 in the above equation. It becomes sigma y of x0 equal to sigma n equal to 1 to infinity Bn sin n pi by L x into cos 0. Cos 0 is 1. So which is equal to sigma n equal to 1 to infinity Bn sin n pi by Lx. But y of x0 is given as a sin pi x by L. Then expand the left side. It becomes, that is, you give values for n, b1 sin pi by Lx plus b2 sin 2 pi by Lx plus b3 sin 3 pi by Lx plus etc. is left side. But right side equal to a sin pi x by L, which is given condition. Then next we can compare the left and right side. b1 equal to a, but b2, b3 all are equal to 0. So the solution of the wave equation becomes y of xt equal to a sin pi x by L cos pi ct by L. all other terms become 0. So this will be the required solution.